Okay, so this is the currents ratio, N1 by N2 is equal to V1 by V2, that is equal to V1 by V2 is equal to I2 by I1. So these are the primary turns and secondary turns of primary and secondary coils. V1 is the terminal voltage, right? The applied voltage at the primary and terminal voltage at the secondary. E1 is this induced voltage at the primary, whereas E2 is the induced voltage at the secondary. Normally, this E1 is less than V1 because if you apply some voltage, from there some drop has to be deducted, then only we will get E1. In the case of V2 and E2 is normally higher because by the time it reaches the terminal, the voltage is dropped because of some resistive components. And the last relation is the I2 and I1. Okay, I2 is the secondary current and I1 is the primary current. So the reason is, as we have said before, it is a static device. There is no moving part or something. So I can state that the primary power, okay, the primary power always equal to secondary power. For a transformer, secondary power. Transformer never add anything actually, it is just transforming. So power will be transformed from one side to the other side, that's it. So you can say that in this side we have V1, I1. Here will be what? V2 into I2. Correct? So if you just move these terms, for example, if you bring this term V to this side, correct? So we get what this side is V1 by V2. What about the other side? What do we have here? I2 will be there, so it's going to be I2 by I1. Correct not? Because this V2 is moved here and this I1 is moved here. So the relation is what? V1 by V2 is equal to I2 by I1. Or otherwise you can say that if you are increasing the voltage in the primary, right? Voltage in the primary and decreasing this voltage in secondary, which means it's like a step down transformer. So what is going to happen? To make the power constant, the current has to increase. So this current has to increase, this current has to decrease and this current has to increase. When you multiply, you must get the same figure here. As if suppose we have 100 times 2 is equal to 200, right? 100 times 2 is 200. And let us assume that here is equal to what? 200 times 1. Both are same, right? Now suppose if I am going to drop this one, right, to 50, then naturally, to make this, the 200 same, I have to multiply here by 4. So this will make, the change. For example, if you are increasing this is dropping this is 50 to 400, right? Definitely you have to adjust the other one, accordingly. So, okay. So this is the basic rule, which means that if you are trying to do one here, definitely it is going to affect in the reverse manner. If it is increasing, the other will be decreasing and vice versa. So this is also one of the important, relation, which is for the tensor relation. Now based on that, we are also going to solve some problems here. Okay. So power is always constant. Input power is equal to output power. Okay, so the transformer is connected on no load, and which means the terminals, the second terminals are open, and we are going to feed some voltage at the input, and this input ammeter which shows some amount of current. So the question is that why such a current? So now if you look at the core, when you are going to apply what you call primary voltage, what's going to happen? The first thing is that there must be some amount of flux is set up here, correct? There must be the flux will be set up. That flux is normally equal as Y, right? So that will take some current, right? So the current which is corresponds to to set up flux in the core is normally called as the magnetizing component. So one part of the input current is nothing but magnetizing component, and normally it is indicated by IM. So this part of the current is responsible to set up what? Magnetic flux on the core. Right? Then the second part, this is the first part here. The second part is, definitely there are some losses, right? The core loss, some of the loss, whether yet fully charged, fully loading or not, there must be some loss will be there. Okay. So there are other components. The second component is to meet some fixed amount of loss, fixed losses. So this component normally we call as the working component. Okay. Normally it means some of the core loss of the transformers. So that is indicated by what? IW. So we have got two components here. So if you look at the no load component I0, then we can divide into two sections here. One is called IM, another one is called IW. Okay. This component is called to meet the loss, whereas this is to magnetize the core. Magnetize the core. Okay. Just copy. Okay, so let's see how we measure the IM and IW by using this particular setup. Okay, so what you can see here, the single phase transformer we have powered by the voltage AC source. V stands for the voltmeter, W is the wattmeter, and A is the ammeter. It is under no load. So no load means the power will be very small. Okay, so let's say the no load reading of the wattmeter W0, and that W0 should be equal to V0 I0 cos phi 0, because it is AC power, right? V0 is the voltmeter reading, I0 means the ammeter reading, and cos phi 0 is the power factor, correct? So since we have V and I, these two are known, even W also known, so you can directly calculate what is called cos phi 0. Cos phi 0 is nothing but W0 divided by V0, correct? From that we can calculate phi 0. Phi 0 is nothing but the no load phase angle. No load phase angle, correct? Now based on that we are going to draw a phasor diagram. So a phasor diagram or a vector diagram. So I'm just drawing now a phasor diagram. This is a vertical axis here, and assume that we are applying V1. Okay, so there is a middle line here. So this I am marking is V1. Now, because now let us look at this way. Okay, you know what is E1, right? E1 is the induced EMF in the primary. And what is the reason for this induced EMF, or who introduced? Helped induce the E1? It is nothing but V1, right? So there is a law called Lenz's law. What Lenz's law called? Lenz's law states that the induced EMF always opposes the cause. So that's the reason. Since it is V1, E1 is due to V1, so that's why E1 normally appear the opposite side. This is E1. So let us assume that E1 exactly down, and I just mark little less because normally V1 is slightly more. Okay, so just mark slightly different. Okay, that's it. So this axis is something called flux. So this is flux here. Okay. Now we have to mark I0. What is I0? I0 is something but the no load current, right? So I am going to mark with reference to V or V1, because I0 is the current in the primary, right? So what is the phi 0 indicate? The phi 0 is the no load phase angle. It is nothing but the angle between V1 and I0, right? So which means I am going to draw an angle here, which is nothing but I0. This angle is called phi 0. Why from here? Because it is between voltage and current, correct? So this is the phi 0 value. Now what I have to do? I have to cut this is into two components here, one horizontal component and one vertical component. So if this angle is phi 0, correct, and we have a vector here, and this vector we can divide into two components. What are they? One horizontal component and one vertical component here. Okay, just copy it out first, then we'll move. Okay, so what you have seen now, this is the I0 and the angle from V1 to I0 is called phi 0. Now this vector we divide into two, one component, there is a component here and there is a component here. This component is next to the what you call the voltage, right, or the what you call the vector. So this is the if this is the angle, then this is called the what you call the adjacent angle, and this normally called as the I0 cos phi 0, because if you calculate the cosine of phi 0, it is nothing but the opposite, sorry, adjacent side by hypotenuse, correct? This is the adjacent side and this is hypotenuse. Normally cos phi 0 is equal to, if you take cos phi 0, adjacent side by hypotenuse. Hypotenuse is what? I0. Adjacent side is what? This side, right? If that side is IW, let's say, okay, this side is IW, let us look at this way. So this is going to be what? IW, this divided by hypotenuse, which is I0. So what is IW? IW is equal to I0 cos phi 0. So IW, that is nothing but I0 cos phi 0. And there is another component which is the opposite, if you see this angle, the opposite side. So to get that, we have to calculate what is called sin phi 0. And I am assuming that this is Im. This is going to be what? Im divided by I0. Right, same thing. If you see this angle, the sign will be what? Opposite side. Opposite side is this, right? This means exactly this, which is Im divided by the hypotenuse. So what do you have? Im is equal to I0 sin phi 0. So we have both the relations we got it now. One is the IW. We found IW is equal to what? I0 cos phi 0, and Im is equal to what? I0 sin phi 0. These two combined will give you I0. But that I0 is obtained by, because since it is a vector addition, so you have to square this and you have to square this, then under root. So if you do that, what happen? IW square means what? IW square will be I0 square cos square phi 0 plus I0 square sin square phi 0, right, under root. Since I0 is a common term, if you take it out, right, within bracket you have sin square phi 0 plus cos square phi 0. What is sin square phi 0 plus cos square phi 0? It is normally 1, right? So if you see the square inside the square root we have I square, so which means that if you add and square them, you will get the answer I0, correct? Because this part is 1, so the answer will be what? I0. So I can conclude in this way that these vector sum of these two components will give you the I0. Okay, so just copy it on that. Okay, so now let's see what will happen if you are going to load the transformer. Okay, so as we have seen before, when it was under no load, the current was I0, correct? No load current was I0. So what are you going to do? We are going to add load on the secondary side. So when you attach load on the secondary side, definitely what is going to happen? I2 will set up, right? Depending upon the load, we have I2. So what is I2? I2 is nothing but the secondary load current, right? Because you are already loaded, and you can get it from where? From the ammeter A2, correct? But where this current is coming from? It is from the primary, right? Not because this current is supposed to come from primary, because there is no source which can deliver to this except what you call the primary. So whatever extra current that is going to be derived from the primary only, correct? So the moment you connect, okay, there is something called a secondary ampere turns, secondary ampere turns, the amperes into the turns, which is normally we call as N2 I2 will set up a flux. N2, because ampere turns is something but a flux, that will be set up, whose direction will be exactly opposite of this. Why? because of the Lenz's law, correct? So you have, what happened, phi is already there. Because of this N2 I2, you will have a MMF or magnetomotive force or a flux in this particular direction, which is given by what? N2 into I2, correct? And again, this I2 is derived from the primary, correct or not? So the primary current will boost, will increase because second is, demanding something, right? So what happened? In the primary, there is a new current will set up. That current is nothing but I1 dash. What is I1 dash? It is nothing but the current, extra current, right? Or the new current, right? The current due to what you call the secondary load. Current due to secondary load, correct? And this current has got two parts here. This I1 dash has got two parts. What are the parts? Earlier we had something called I0, right? That's always there. In addition, you have some current called what? I2 dash. What is I2 dash? It is nothing but a current in the primary due to secondary current. Okay. So this I2 dash can be defined as, it is nothing but a current at the primary due to I2. Or in other words, I can say that it is something but a transformed current, right? Or transferred current, right? Transferred current from where to where? From secondary to primary. Correct? So because of this extra current, right, there is again another ampere turns in the primary. Okay? So what is the AT, which is ampere turns at the primary? Ampere turns at the primary will be what? We have a turns of how much? N1 and I2 dash, correct? Because I0 is already there, I am talking about the extra current is I2 dash. So N1, I2 dash is the new, what you call, ampere turns in the primary. That is equal to what? N2 times I2. Because N2 times I2 is the new ampere turns, right? In order to counterbalance this N2 I2, you will have in the primary N1 I2 dash. Now, what is the direction of this N1 I2 dash? It will be exactly opposite here. Right? So this part, this arrow indicates N2 I2, whereas the top one indicates what? N1 into I2 dash. They both cancel each other because they are in the opposite direction. So when this cancel with this cancel, what happened to flux? Flux will remain the same. So initially you have flux phi, right? The moment you load this one, N2 I2 set up, correct? Then immediately what happens? N1 into I2 dash will be also set up. Their magnitudes are equal, but directions are opposite. These two cancel. So that's why always you can see that whether you load or unload, always the flux is maintained as constant. This is normally one of the important questions you may get it. What is the question? Why the flux is always constant, right? In the primary, whether you load case or unload, full load or no load. The reason is there are counter what you call ampere turns. One is due to N2 I2, other one is what? N1 into I2 dash. Okay, so just copy down this. So this is an important thing. N1 I2 dash is equal to N2 I2. So here N1 I2 dash is N2 I2. You can calculate I2 dash in terms of N2 by I1 times I2. And we are assuming that the value of N2 by N1 is K. Therefore, I2 dash is equal to K times I2. So let us try to draw the phasor diagram of transformer and load. So here we are considering UPF. What is UPF? Unity power factor. Unity power factor, which means cos phi is equal to 1, right? Or phi is equal to 0. Correct? So there is no phase angle between current and voltage. They are in phase with each other. Okay. So let us assume that this is our phasor diagram as we have said before. So here we have flux, here we have E1, and let's say that we have E1 and E2. And already we said we have a current of what? I0, which is also called the no load current, with a angle of phi 0. Correct? Now we want to find out, the I2, because now the load, the transformer is loaded, right? And what is the secondary current? The secondary current, let's say it is I2, okay? I2. And I2 is going to be here, right? Because with respect to E2, because E2, V2, everything will be coming in this particular line. So what I'm going to do, I'm going to draw I2 with an angle of 0. So which means that I'm going to get something here, right? Let us assume that this is I2. Assume that this is I2. Correct? So this is the secondary, right? Now I want to get the effect on primary. So what is the corresponding current which is available in the primary due to I2? Which is I2 dash. Correct? So, and what is the relation I2 dash? I2 dash is equal to K times I2. And K is a factor. Correct? So what I'm going to do, I'm going to, project this particular I2 on the primary side, because primary side is V1. So I'll get something here which is I2 dash. Correct? So now we have both, right? I0 is there, I2 dash is there. Now we want to add them, right? You cannot simply add. Why? Because they are not in the same angle, correct? So what should I do? I should add vector addition. So I'm going to take I0 this and I'm going to add here. I'm going to take I2 dash here and I'm going to add here. So what I'm going to do is, I'm going to draw a line here, I'm going to draw a line here. Okay, this line is I0, this line is I2 dash. Then I'll get something like this. So this is nothing but the vector sum of what and what? I0 and I2 dash. This is something called I1. This I1 is the effective primary current. And then now we have a new angle here. That is supposed to be the load power factor because of the UPF calculator. You get the point? So this is the the phasor diagram of a transformer with UPF, unity power factor. Correct? So this particular. So phi is the primary, the power factor angle. Power factor angle. I1 is the primary current. Okay, with UPF load. Okay, output. Okay, and what we can also see that I1 is nothing but vector, this dot indicates vector. It is nothing but I0 vector plus I2 dash. So what will happen if the load is lagging or the inductive? So the same, so we are going to mark here is V1, E1 and E2 is supposed to be here, and this is flux, right? And already we have I0 with an angle of I0, correct? Now the lagging. So I am going to mark lagging here. Normally it was here, right? UPF. Lagging is supposed to be with an angle, and this angle is the phi 2, which is the load power factor, okay, reflecting on the in the secondary. That's why this angle is phi 2. Phi 2 is the angle between I2 with respect to E2 or V2, whatever. Okay. Now what we have to do? The same I2 we have to reflect to the primary. So what you have to do? You have to extend this line in the opposite direction. So then I will get something here is called I2 dash. Now what should I do? Like what you have done before? You have to add this one here and add this one here, right? I'm going to go like this and go like this. I'll get the result like this. So this is supposed to be I1, and this is supposed to be what? The new angle, which is phi. Okay. So this is happened in the case of an inductive load. Okay. This topic. So in the case of leading, okay, we'll go for the same. So first thing is we are trying to draw I0 with an angle of phi 0. Then the leading, right? UPS was exactly on the line. Lagging was here. Now I'm going to go for leading, supposed to be here. So let us say this is phi 2. That makes an angle of what? Phi 2, right? Leading angle. Then what is going to happen? The corresponding value, I mean the reflected on the primary will be something like this, correct? Which is I2 dash. Then, as we said before, you are going to, extend it like this, correct? This is here and this is here. Then you are going to complete this. You have I0, right? So then we'll find a very small angle here, right? That is the resultant angle. Sorry, it's supposed to be I1. Yes. So I2 dash, I0 and I1. So we are trying to look at different components, resistive and inductive components of the transformer, and we'll try to model a transformer here. Okay. Now what we have seen? We saw the transformer. We have a primary coil here, and we have a secondary coil. That's it. In such case, this transformer we can call as it is nothing but an ideal transformer. Ideal transformer means a transformer without having any loss, right? But practically speaking, there are many other components out there. Okay, the first component, which is responsible for I0. You remember we have seen that whether the transformer is loaded or unloaded. There is some normal, what you call no-load component is there. This no-load component has got two parts. Okay, one is called R0, other one is called X0. This R0, the current through the R0, because R0 is a resistor, right? Something a loss. So that's why this component is called what? IW. And X0 means it's like a coil. Coil always magnetized. So this is called IM. And if you just vector add these two, what will you get? You will get I0. So this part is called the no load circuit. Okay. No load, circuit or transformer. Only that part. No load. I can say no load component. Okay. No load component. No load circuit. Fine. Then what else you can see? You can find that transformer has got some resistance. It also has got some leakage reactance. Since it is happening in the primary, I'm going to say this is R1, this is X1. Okay, here only we are applying the input voltage, which is V1 here. So this is the primary side. R1 is called the primary resistance. Primary resistance. And X1 is called primary inductive reactance. Inductive reactance. Okay. Same manner, if you look at the secondary, we have R2 and we have X2. Then we are supposed to connect our load. Depending upon the load, it could be like what inductive or capacity something. So this is supposed to be R load. Okay. This is R2 and X2. So R2 stands for secondary resistance and X2 stands for secondary inductive reactance. Okay. Transfer of secondary circuit to primary side. Okay, so this is what we done. So what you can do, we can start from the input side. So we have V1 here, right? Then we have R1, we have X1, we have an inductor part here, and we have a resistor part here. No change, okay, of these parameters. Okay, as we have seen before, IW, IM, I0. Then what is going to happen next is what? We are transferring this value to this side. So I'm going to add here one resistor. It's going to be what? R2. Since I transferred to the primary, I'm going to say R2 dash. And the same manner, I'm going to say this is X2 dash. Load, right? You have got two components in the load. Suppose if it is RL and XL, correct? The load. Then I'm going to say here RL dash and XL dash. Okay? This is going to be our transfer load. So our equivalent will be something like this, right? These are the all primary circuit and the secondary circuit all transferred. Now you can do one thing here, okay? If you see what is the corresponding, the relations, how do you get the R2 dash values and R. So when it is in the secondary, what was the drop, copper loss in the secondary? It was I2 square times R2, correct? When the coil, when it is like in the secondary side, it was I2 square into R2, right? Now, when you move the same thing to the primary, what happened? Now, this current is become what? This current is I1, correct? I1. So, the primary current square multiplied by the value become R2 dash. With the point. Because we just move the resistor from this side to this side. When it is here, the current was I2. When it is moved here, the current become I1, correct? So what you can do, we are interested in R2 dash because we know R2, right? It can be measured. R2 dash is something, but right, if you just keep that one, this will go down, right? I2 by I1 whole square times R2, correct? So what is I2 by I1? Already we have seen N2 by N1 is K, correct? So if that is the case, what will be I2 by I1? 1 by K, correct? So we can say it is equal to R2 divided by K square. So always you remember, when you transfer the secondary value to the primary side, you are supposed to divide the secondary side to primary side, you have to divide the secondary resistance by the square of the transformation ratio, which is K. So this is going to be R2 by K square. Okay, this is also one of the important relations to remember. So likewise, so if I say this R2 dash, this will be what? R2 divided by K square. This will be what? X2 by K square. This will be what? RL dash by K